Okay, welcome everyone to HO Colloquium. Today, our speaker is Fallon Kono from Georgia State University, and it is my great pleasure to introduce Fallon Kono. Fallon is a fifth-year graduate student in a dual program between Georgia State University and the University of Rome Sapienza. Currently, she is a NASA Finest Fellow and a Second Century Initiative Fellow at Georgia State University. In 2022, she served a year-long internship at JPL developing a new helium magneto-optical filter. Currently, Fallon splits her time and research efforts between Rome and Southern California, where she works on developing a new network of ground-based space weather telescopes called GATES. The GATES network consists of two magneto-optical filter-based telescopes, which Fallon is working towards getting fully operational by the end of 2025. Outside of research, Fallon is very passionate about outreach and STEM accessibility, serving as a graduate lead for the Georgia Outreach Team for Space, the social media manager for astronomy on TAP Atlanta, and the science student representative from 2022 to 2024. Today, she will be speaking on GATES, a network for synoptic space weather observation. To Fallon.
Great, thank you for that.
Share your
Yes,
slides.
I will share right now. I want to apologize in advance. I'm fighting a bit of a head cold, so if my voice cracks, I thank you for ignoring it, and I'll push through. Can you see my slides okay?
Yes.
Okay, great. So, thank you again for the introduction. Again, my name is Fallon Kono. I'm a graduate student at Georgia State, University of Rome Sapienza, and I'm going to talk to you about GATES, which is a new network of ground-based space weather observatories. And it is a collaboration between lots of different schools, institutions, private companies. So you see a bunch of logos for down at the bottom. So I want to do a quick outline of my talk. And my talk is divided into three questions: why, what, and when. And specifically, we're going to start with why we care about space weather and why we should use networks, and specifically GATES, to study space weather, why GATES is targeting multi-height observations, why we care about that, and why we should use MLFs, before moving on to the what, which is what is GATES itself, what's the current status of our two locations, and what are some of the science goals we're trying to target. And then the question that probably all of you care about, which is when will we be up and running? When can you use the data that GATES is going to be producing? So with that, let's move on to whys and start with a nice introduction for why we care about space weather. So space weather are any of the eruptive events that happen on the sun that interact with the Earth. So things like flares, coronal mass ejections, solar energetic particle events. And we care about understanding and predicting these events because they can have really detrimental effects to things on Earth and in space. So they can degrade satellites, which can interrupt satellite and radio communication. They can pose a lot of radiation threats to astronauts in space, and in the era of Artemis, with a lot more people in space, and even high altitude planes that can cause a bit of a radiation issue that we want to prevent. And on Earth, in our continually globalizing, digitizing world, having radio outages and satellite miscommunication can cause big issues. And on top of that, in more extreme endeavors, it can cause power outages, which can be incredibly detrimental, and not just for communication, but for life for everybody. There are some positive effects. Space weather events and flares can cause things like aurora, which are really pretty to look at. But even in the case of these nice events, we still want to be able to predict them because we want to know when we can go look at aurora. And on top of understanding why it's really important for humans that we can predict space weather, our sun being our closest star, we want to understand the mechanisms for these events so we can use it as an analog to other stars. Because other stars, like M dwarfs, flare even more. So understanding what is causing these events so we can protect ourselves on Earth, but also understand other stars is very important. Now, when we're looking at space weather events, it's important to have continuous or synoptic observations because we want to look at a long-term change in the sun. And there are a couple different ways to do that. You can do that from space with satellites, but that can be very expensive. You can do it from the poles and Earth because the sun never sets for a good portion of the year, but then you're limited to only half the year. or you can do multiple sites at low latitude on Earth, so you can combine them into a network. And that's what I'm going to be talking about, why we can use networks. And I want to start with some historic networks. Let's start with GONG, the Global Oscillations Network. This is probably a network that is most known for doing solar observations and one of the most popular to use. So GONG has been operational since 1995 in some capacity. And GONG is utilizing multiple, again, low latitude sites to, when combined, have fully synoptic observations of the sun when they're all operational. And so GONG is showing us that networks can be very beneficial for ground-based synoptic observations. And one benefit to networks like GONG, you see in that bottom left of the image, an image of the not dome, but enclosure for the telescopes. They're smaller, they can be more easily accessed and maintained, and so ground-based sites are beneficial for that purpose. Another ground-based observatory that I want to talk about is SOLACE. This is the Synoptical Optical Long-Term Investigations of the Sun, and it was developed in 2003. And although this is an instrument, not necessarily a network, it is showing again the importance of synoptic observation that's been recognized by the solar community for decades. And so these two are older instruments and networks showing that this has been a long-standing interest of the solar community. And I want to talk about a newer network called SAMNET. SAMNET stands for the Solar Activity Monitor Network, and it is also magneto-optical filter based. I'll talk about magneto-optical filters in a bit, but I wanted to bring up this network because it is currently in the developmental idea stage, showing that not only are the idea of networks still very popular for studying space weather, but magneto-optical filters are gaining more traction as recognizable, useful scientific techniques. And so with these networks and instruments building up, we come to GATES, or the Global Automatic Telescopes Exploring the Sun. I will say that quite a few more times in the talk in case you miss it, but this is the network that I'm working on, and it's leveraging the power of a GONG-based multi-site network to SOLACE's synoptic observations and SAMNET's idea behind magneto-optical filters to form a new network. And so the image you see here is a nice little map that's showing where our telescopes will be mounted and some of our main university collaborators. So GATES, Global Automatic Telescopes Exploring the Sun, is currently a dual node ground-based space weather observatory. Our first node is in Apple Valley, California, that blue point all the way on the left. Apple Valley is about 90 minutes northeast of LA, so just think LA, but in the desert, so less fun. More fun for telescopes, though. And our main university collaborator with California is Georgia State. And then our second telescope is out in Europe. It's currently in Rome at the University of Rome Tor Vergata, but it will be mounted in the Canary Islands of La Palma, Spain. So that's that second blue dot that you see off of the western coast of Africa. And we are given a location to mount there because of University of Rome Tor Vergata's collaboration with the Telescopo Nazionale Galileo. And so this is what we're trying to do. This is what GATES is. And why should we care about GATES, though, as opposed to, let's say, SAMNET? And one of the main reasons is the history behind GATES. And specifically, I want to talk about the history of the MOTH group using magneto-optical filters. So MOTH stands for magneto-optical filters at 2 heights. And the MOTH group consisted of people like Dr. Stuart Jeffries, Dr. Phil Murphy, Dr. Francesco Pavilli, and basically all of my advisors that worked with magneto-optical filters sent down to the South Pole to use Doppler and magnetograms for space weather observations and study. And so images you see on the left are potassium and sodium Dopplergrams taken from the MOTH instrument back in 2003. These are taken from the South Pole. And the MOTH instrument was able to have full Doppler and magnetic field capabilities, observing in both potassium and sodium. The MOTH group also has had a very long history developing other types of filters. Notably here, you see a helium-1083 and calcium-440. These are both filtergrams, which means we have not been able to fully develop for velocity or magnetic field observations, but we just have the intensity images of these magneto-optical filters. So the longstanding history developing this technique and using this data reduction is one of the reasons why GATES is posed to be such a useful network, because we have the infrastructure already set up to deal with this data. So I want to talk about MOTH growing into GATES and start off with the instrument itself. So this is the MOTH instrument. You'll see there are 2 channels. Sodium is on the top and potassium is on the bottom. And again, this was launched down into the South Pole for a few different data runs, actually spanning from 2001 to, I believe, 2006. And so this image itself is back in 2004. And this instrument produced those Dopplergrams that you saw on the previous page. These Dopplergrams themselves can be found in Aparna Venkataramanasastri, a former Georgia State graduate student's publications. And she worked with this data from the South Pole to investigate the usefulness of Dopplergrams and specifically acoustic travel time for space weather. And so here is a plot of one of the works she's done. And this plot has a lot of lines on it, a lot going on, but I want you to focus. Blue is a non-flaring region, green is a flaring region, and that red line is a flare. So what we're looking at is time leading up to a flare and phase travel time of acoustic waves. And so what you see about 6 to 8 hours before that flare goes off is this drop right here in travel time. And so what Aparna has found using these Dopplergrams from the moth data is that there's some change in the acoustic wave travel time before a flare. Now, if you've been listening really well and you know the solar cycle, you know 2003, 2001 data is not the highest energy level for the sun. And so Aparna's data set did not have a statistically significant number of flares to be able to say, yes, this is definitely a method we can use to predict flares, but it does provide tantalizing evidence that maybe we should investigate acoustic waves in relation to space weather. So that's one of the things that Gates is trying to do, is to build off of the data sets and the science of the moth instrument to see if we can use these different techniques to investigate space weather. Now, in order to do observations like this, doing wave travel time, we need more than just one height of line of sight velocity. We need multi-height, which is where that potassium and sodium comes into play. So we stack them up, and the images you see on the left are now no longer from the moth instrument, but are from Gates itself, the node out in California. And the plot on the right is just showing color coordinated what heights we're looking at in the atmosphere with the Gates telescope. So just like moth, Gates has a potassium and a sodium channel. Potassium, we use the 770 line, which corresponds to about 400 kilometers in the solar atmosphere and the quiet sun, so about the photosphere. And then the sodium D2 line, we have the 589 line, which corresponds to about 700 kilometers in the solar atmosphere. So with just these two channels, which we have had in the past, we're able to investigate travel time between these two heights, the difference in velocity of waves, these two heights, the difference in magnetic fields. So we're able to get things like wave travel times or frequency plots, which is really exciting and allows us to do these investigations into acoustic waves and also just general analysis of space weather. But I mentioned before that Gates is trying to grow and build off of moth. So if we were just going to use the same instrument as moth, why wouldn't we do that? What Gates is trying to do is to develop another filter, specifically a helium filter, helium 1083, to go up higher in the chromosphere. And so the helium-1 1083 line corresponds to about 2,000 kilometers in the quiet sun. And so that gives us upper chromospheric observations, which would allow us to not only investigate a larger portion of the solar atmosphere, but investigate specifically the chromosphere, which is very exciting for scientific reasons of some of these signals might be stronger higher in the atmosphere. They might not reach the higher atmosphere at all. And the chromosphere having fewer emission lines than the photosphere does, being able to probe the chromosphere gives us much more exciting, in my opinion, science. So this is what Gates is trying to grow into, to have 3 different heights in the solar atmosphere and to investigate things, excuse me, like those phase travel times or just in general acoustic waves. So I want to talk a little bit more about acoustic waves in the solar atmosphere and one of the first science targets that Gates is looking to cover. And so when I talk about acoustic waves in the solar atmosphere, I need to talk about the acoustic cutoff frequency. And so this schematic you see on the left is showing what the acoustic cutoff frequency is in the solar atmosphere. At about 5.2 millihertz, we see this cutoff, above which waves are free to propagate and we can observe them, and below which they are reflected back. So we aren't able to observe lower frequency than 5.2 millihertz. I apologize again, quickly grab a quick sip of water. And so if we were to observe at lower frequencies, we shouldn't see any waves propagating. And I want to draw your attention to this plot, which is from Finsterly et al. 2004 using moth data. And what you're looking at is a power spectrum of about 4 millihertz. So 4 millihertz below the acoustic cutoff frequency, this entire plot should be green or evanescent waves, neither propagating towards or away from us. In this plot, blue is propagating towards us, red is away. And we see for the most part, it is fully green. The difference between these two plots is simply time. The one on the left is t0, the one on the right is 8 hours later. And I want to draw your attention to point 2. At t equals 0, we see a blue point, which means waves are propagating towards the surface. We can observe them, which we shouldn't be able to. It goes back to almost normal at 8.3 hours later, and this region is exciting and interesting because this is a flaring region. So another indication from MOTH data that there is something potentially going on with acoustic waves correlating to flares or space weather events. I'm so sorry. So this, combined with the work that Aparna's done, is telling us this could be a really tantalizing thing to look at regarding space weather. How does acoustic waves affect, my apologies, how do acoustic waves affect the dynamics that lead to these events? But again, in order to get phase travel times or frequencies, we need those multi-height observations. And in order to get them, in order to get these Dopplergrams, we're going to use magneto-optical filters. Magneto-optical filters are a technique that we use to get filtergrams, or red and blue wings with different polarizations of light. What they are physically, you see an image up in the right-hand corner, is a glass cell filled with our ion of choice, placed in a longitudinal magnetic field between two cross polarizers. Magneto-optical filters, as I've been mentioning with MOTH, have been used for a very long time. They've actually been successfully used to observe the sun since the 50s, so they do have a very long-standing history of being used for observation. An MOF-based instrument can have a lot of benefits over other types of instrumentation, such as Fabry-Perot. It has narrow passbands like a Fabry-Perot. An MOF can have 60 milliangstroms of narrowness to a passband, but unlike Fabry-Perot, it is insensitive to acceptance angle, which allows us to have much more wavelength stability and allows us to also simplify our optical design, making our telescopes not only more compact, easier to align, but also just cheaper. Additionally, magneto-optical filters can have very high throughput, in theory just dependent on our polarizers themselves, which allow to have very high cadence measurements to be made. Since I'm talking to you about gates and what we are and how we work, I want to go over the schematic of how magneto-optical filter-based telescopes actually work. So I want to start with our filter section, which is our first MOF cell. And it's utilizing Zeeman splitting and Faraday rotation to create that really narrow passband and give us both blue and red wings. So incoming light comes through our first polarizer, and as it passes through our cell, our Zeeman effect takes into place, giving us red and blue wings, and our Faraday rotation allows just our wings, our wavelengths of choice, to go through that X polarizer. So what we're left with is very finely filtered light in two different wings. Then we come back to the full telescope and we go through our wing selector section. And what happens in just the wing selector section are these two wings, red and blue, go through another cell, which changes our polarization to circular, allowing us to then go through a quarter wave plate, which allows us to select red and blue wings in right and left-hand circular polarized light. What we end up with is called a filtergram. So again, red and blue, right and left-hand circular polarization. This is our whole telescope setup, and as you can see, it's fairly simple. There are a few other optics and filters here and there, but overall a very straightforward, simple optical scheme that gives us really powerful data. So let's zoom in on these filtergrams, and this is data again from Gates. What you're seeing on the left is our sodium filtergram. What you're seeing on the right are the Doppler and magnetograms that we can produce from this filtergram. And so these data, I want to emphasize, are not calibrated. They're taken back in May when California was still working on the calibration mechanisms and scheme and data reduction pipeline. So these are not currently fully calibrated. They're just created Dopplergrams and magnetograms from the filtergrams. I wish I could have included some data from last week because we did run observations all last week, but since we have our calibration set up, which I'll talk about in a few slides, the data is currently still in our reduction pipeline. So here are some lovely images from May where we can see some nice active regions and some good features in our sodium line, so that low chromosphere. So this is the data, the science reason why we should care about MOFs, in addition to the fact that they have simplified schemes and very narrow passbands. Well, another very quick reason I want to mention we should use them is that they simplify schemes so they're more affordable. Our entire telescope is commercially buildable and available. Our cells themselves come from our private collaborator, the EDICO in industry, but they also sell to the general public. All of our parts, even our mount and our dome, come from commercially available places. Most of our parts are Thor Labs, and any small parts that we do make in the machine shop could be made from Thor Labs parts, but also are sometimes easier to make with just little pieces of metal. So our cameras are also commercially accessible, and you see a Daystar telescope in the bottom, which will come into play in Rome. But one node, one channel of a Gates telescope costs on the order of hundreds of thousands of dollars, not millions, not 100,000s. So they're really quite accessible to expand to another node so we can get more coverage over the course of the Earth. Now that was why. I hope I've convinced you why we should care about space weather and why we should observe it and why we can and should do it from the ground with magneto-optical filters. Now I want to move into what. What is GATES, the title of my talk, what is the current status of our sites, and then what are some of the science goals we're trying to target. So again, GATES is Global Automatic Telescopes Exploring the Sun, and it currently consists of 2 telescopes that are in various stages of operation. Our first node, which is the current focus of the GATES development, is in Apple Valley, California. It has a dual channel telescope, and it is located at the Mojave Solar Observatory, or MSO. And our second node is currently out in Rome, and it is the Tor Vergata Solar Synoptic Telescope, which consists of a single channel magneto-optical filter-based telescope and an H-alpha telescope. The observing goal of GATES is to be fully synoptic, so I want to show what our current observation capabilities are. I know there's a lot of lines on these plots, but our red is sunrise, sunset. It just shows solar altitude, and our blue is just height in the atmosphere we're observing. Dotted lines show the TSST, what it will be when it's mounted in Spain. So our European, Rome, Spain node, and then the solid lines are California, MSO. And so currently, our observing capabilities are a dual channel observing in California with sodium and potassium, and a just potassium out in Europe. And these plots are shown on the equinox. So on the equinox, GATES will have 21 hours of coverage with about 4 hours of overlap between the 2 sites. This means that in the summer, we do have a full 24 hours of observing with just 2 sites. And one of the benefits we currently have with having a potassium channel accessible in both locations is that we can more easily use it for calibration between the 2 sites with those 4 hours. Now, I've mentioned that GATES is trying to develop into a larger suite of filters, specifically using helium. And once we're able to finish that development, we will upgrade the California telescope to include that helium line. Now, you might have noticed the potassium line in California sadly has to go away when we introduce helium, and that's because of just current financial and mechanical limitations to our mount. But one of the really big benefits to replacing the potassium channel with helium is that all of our optics are currently coded for potassium 770 will work with the same efficient throughput for helium 1083. So we don't need to replace any of our optics. We can simply switch out our cells and realign our focus for our camera, which means that not only is that saving us money, but if we ever need to replace our potassium cells again for calibration, we can do that. And a benefit to replacing potassium over sodium in California is that having a sodium and helium observatory gives us a fully chromospheric observatory to again investigate those differences in the chromosphere as opposed to just the photosphere. And also, we still have that potassium from Europe, so we'll have, for those 4+ hours a day, having 3 heights of observing, and at least 2 at all times in California. And you'll be saying, Fallon, that's not bad, but at one point you only have 1 height. Can you do any better? And I would say we can throw in some HMI data. We are currently setting our cadence and our resolution to try to be very easily scalable to HMI, so we can use their magnetograms with iron, so that way we can, for 4 hours, have 4 heights, or as long as 1 telescope is up, have multiple height data, which is very exciting. So now that you see what our ultimate goal for our observing is, I want to go into each node individually, starting off with California. And again, I'm starting with California because this is our current focus of the GATES development, specifically because this is where I'm currently working. So our first node is located in Apple Valley, California. Again, that's about 90 minutes northeast of LA at the Mojave Solar Observatory, the private research observatory of our industry collaborator, the Eddy Company. And so what you're seeing here is our dome itself, and then inside we have our lovely telescope. So the Mojave Solar Observatory, or MSO, currently consists of a dual channel on-sky observing telescope that again has that sodium D2 589 line, and the potassium one, 770 line. And these are the same lines that the MOTH instrument used, but the completely different cells, completely different instrument itself. MSO has a 70 millimeter aperture, and respectively, the resolution between the potassium and sodium are about 0.44 and 0.43 arc seconds per pixel. So we are getting full disk observations, and with the resolution of that, we're getting really good sampling across the disk. Now, I did report the aperture in millimeters, but if you have very good eyesight, you'll see this measurement is in inches, so don't be thrown off. This one's in America, so our measurements on our design are in inches, but we are very careful to double check our conversions. Currently, like I said, MSO has full data taking capabilities. What you see here are Doppler and magnetograms for the sodium and potassium channel, again, taken back in May. Our images from last week are still processing, so we do have data taking capabilities currently, even though the images you're seeing are from a few months ago. What we've been working on from May till now has been calibration. And I want to talk quite a bit about calibration because this is a lot of the work that goes into building a new network and what we have been focusing on. This image you see, the schematic is from Forte et al. 2020, which is the data reduction pipeline for the Tor Vergata Solar Synoptic Telescope, or the other node of the Gates network. So we're trying to build off of already set instrumentation, data reduction pipeline science so that we can really make Gates ready, up and running as quickly as possible with really great science. I want to zoom in on level 1, level 0 data because this is what has been giving us some of the most issue. And your level 0 data are things like raw images, your flat fields, your dark frames, and your leak through polarizers and stuff. And in our case, ancillary temperature data, which corresponds to the temperature our cells are running at. And so what we have been working on is specifically our flat fields. This is an image here you see of flat fields we've taken from the sun. What differs from our techniques for flat fielding from nighttime observing flat fielding is we do not have a strong enough source other than the sun to actually have enough emission on our detectors that we can actually use them. So whereas in nighttime observing, you can do sky flats or dome flats using a halogen lamp, with the sun and with our very narrow band filters, we needed to use the sun with a diffusive filter in order to actually have high enough counts. So this is a flat field taken from about 3 weeks ago, and with it, we're able to continue on through our data reduction pipeline to get not only really clean calibrated raw data, but get to those final magnetodopplergrams. So once we get through that level 0 data, we get to level 1, which does all of these corrections, and then we need to do registration errors. So when we're creating Doppler and magnetograms, we're stacking together multiple wings, red and blue, of filtergrams. So an error that we often run into is this white halo you see on the right side of the Dopplergram, meaning that simply our red and our blue wings are very misaligned and we need to line them up more properly. And so this data reduction pipeline has already been created for the TSST, Tor Vergata, but we needed to adapt it in order to properly work for our data. So this is something that we've been working a lot on and that is currently running and testing today. So hopefully by sometime next week, we'll be able to actually see, is our data reduction pipeline working to fix this registration, which we need to do all of these steps before we can do any science investigating what's going on with the magneto or Dopplergrams. So this is a really important step that is very tedious, but is making Gates a better network. You would be saying, that's great once you've calibrated, but what are you doing to actually move around this data, and how are you getting these telescopes up and running in general? So I want to talk about remote access to our telescopes and the transferring of our data, because the A in Gates, I'll remind you, is automatic. And the first step to an automatic telescope network is remotely accessible. So these images you see here, I wanted to show because this is me fully remotely accessing and controlling our telescope and grabbing data while I was on a flight over the Atlantic Ocean. So although my Wi-Fi might not have been great, I was still able to control our telescope, which I thought was really cool. And so currently our node out in California is remotely accessible and controllable all throughout the day. We are working to get it fully remotely accessible. Currently, there is still a few manual things we have to do at the end of the day to reset for observing the next day. But our ultimate goal is to be able to show with MSO that we can remotely and automatically then access our telescope so we can then continue to develop the Gates nodes with that in mind. The technique we're using to remotely access and move data is TeamViewer. It's a free app that is currently available in both countries, and we're choosing to use this so that it is more accessible to all of our different nodes. Ideally, in the future, hoping to scale up to something a little bit more sophisticated and a little bit quicker of data transfer rates. Our current rates are on the order of about 4 megabytes per second, which might seem like brutally slow, but is actually plenty fast enough for over the course of the day what we'll be observing. But you might be worried about that because you might be thinking, Fallon, if you're observing the sun synoptically, you're going to have a lot of data. How are you moving that and how are you storing it? And so I want to talk about our data storage and distribution. The image you see on the right is showing our 3 computers and our multiple other analog control devices for everything that goes on in the telescope out in California. We have 3 computers because one controls data reduction, dome control, and data storage, and the other 2 individually control the potassium and the sodium lines. Ultimately, we want to be able to have all of our data stored on a server in a cloud so that it's accessible for all of our collaborators, whether that be specifically to Gates or anyone that wants to use the data. But currently, due to our budgetary issues, we're storing them on hard drives. And so the process that we're actually doing to get the data looks something like this. On day 1, we're taking data that is stored on PC 2 and 3 that again control the different channels, sodium and potassium of the telescope. Now, these computers themselves have 16 terabytes of storage, and given the fact that, let's say we're having a cadence of about 5 seconds, so we can investigate those high frequency waves with a 15.4 megabyte filtergram. Let's say we have 8 to 10 hours of observing and 15% overhead. Each MOF channel produces 0.2 terabytes per day. So with that 16 terabyte computer, it has no problem holding on to at least a day or 2 or multiple days worth of data. Then over the course of the night, we transfer all of the data from computers 2 and 3 to 1, and we do this via TeamViewer. And although it would be a little bit quicker to hardwire in and transfer data over, we are choosing to use TeamViewer at this time to have a consistent setup of data transfer because we cannot hardwire data transfer from California to Rome. So over the course of the night, all of the data is transferred to computer 1, where the next day, computer 1 calibrates our data, saves it onto our hard drives, and does some preliminary reduction, while computer 2 and 3 are taking data the next day for the next level of telescope. And again, with our current setup for our cadence and our storage capabilities, we have enough storage as it is for about 300 days of observation, or 150 with a full backup, which we're hoping is more than enough time to show proof of concept that our network is working and then have more access to more sophisticated and more generally accessible data storage techniques than just our hard drives. But as of right now, this has been working really well for us, and we're hoping to use the data storage in this method for the first 1.5 years of Gates. If you tuned out the last 10 minutes of my talk while I was talking about data and things, I want to talk about our helium filter now, which is really exciting, so tune back in. I've been mentioning Gates is trying to expand on the magneto-optical filter base, and the way we're trying to do that is to develop our helium filter beyond just filtergram status. And the way we do that is by testing different configurations of our pressure and our ionization power and our magnetic field. So the image up on the right, again, I'll remind you, is what an MOF cell looks like. And the way we develop a helium cell is different than the running technique for a potassium or a sodium cell. So where those are alkaline metals and we are populating a particular line simply by vaporizing the ion in the cell by just heating it up, helium is a gas. So the temperatures we can heat it up to on Earth are not doing a whole lot for it. So what we need to do is ionize the helium in the cell to repopulate back down those lines that we care about. Helium-1 is a metastable line, which means that we need to create a critical population for magneto-optical filter function. But if we go over that critical population of helium-1083, the other helium ions will depopulate it. So that's the test you see on the left, which is what pressure of helium in the cell is ideal for our peak presence of helium-1083. And then the test you see on the right is simply testing what is the ideal power we should ionize the cell at. The pink line is showing when the cell begins to ionize, and the orange is the line we picked because, as you see, it asymptotes off. And we want to work with as low of radio frequency as possible for radiation purposes, but also just so we don't kill out our cell more quickly. And so we have in the lab been able to get another filtergram of helium-1083, like the MOF team had done in the past, but we are still working to get that full Doppler magnetic capabilities. And what that is, given the setup of a magneto-optical based telescope, is the filter section is working, but we're trying to work on the wing selector section. And in order to do that, we need to run a few more tests. So I'm going to do a quick summary of what's going on in California. We currently have a telescope that has data-taking capabilities at 2 heights simultaneously. It is remotely operational, almost fully, but not quite. We're working on helium development, and as of exactly today, we do have some data from last week we're processing. And I know I said we currently can take data, but actually our telescope is being cleaned. I'm going to go back to the lab right after this to finish that up, so we can have an observing campaign after Thanksgiving. And this is because one of our main issues out here is dust, and we are working to improve our mounting box so that way we don't have as much dust issue, but that's what we're currently working on. So after California, I want to talk about our European leg, which I talk about as in Rome, but will be mounted in the Canary Islands of La Palma, Spain. So our telescope is currently still in the lab, which is why it has these 2 locational identifiers. So this lovely dome you see here is not going to be our dome. This is the Telescopo Nazionale Galileo, or the TNG, and we get this nice little plot of grass right in front of the TNG. And the reason we're able to use this lovely space is because, like I mentioned earlier, University of Rome Tor Vergata has a lot of collaborators and a lot of internal people working on the TNG. So we have been in negotiations for a specific location that we're able to mount our dome, whether it be where this arrow is, off to the side, off to the other side of the walkway, because not only do we want to make sure where our view isn't blocked by other telescopes, we want to not block the many telescopes that are on this lovely mountain. And the TNG is also going to be providing us with some power, so we will be fully operational up there pretty easily compared to other telescopes having to build up on a mountain. So this is where the telescope will end up, but currently it's at the University of Rome Tor Vergata in the lab and also on the roof sometimes when I'm running tests. And Rome is where I want to talk about our current status of what TST looks like. So again, Node 2 out in Rome is TSST, the Tor Vergata Solar Synoptic Telescope. I do apologize, there's so many acronyms in instrumentation, but this is our European leg. And it consists of a single MOF channel of potassium 770 and an H alpha telescope that is commercially available. The images you see up at the top are our actual telescope in the lab, and then our model, and then our actual telescope down below for the H alpha. Our H alpha telescope has a 127 millimeter aperture, and its resolution is about 0.21 arc seconds per pixel, whereas our potassium channel has an aperture of 80 millimeters, which is a little bit larger than our aperture in California, which was 70. And the potassium channel has a resolution of about 0.59 arc seconds per pixel. So again, we have full disk observational capabilities with quite good resolution. What we're working on for the TSST currently is alignment. And this is the same lab you saw previously, just one room over, because this is where our CELSTAT hooks up. So we can actually work on alignment of our telescope. And I have been mentioning that I started with California because California is our current focus of gates, and that is also because this is where I'm currently residing. However, I did go to Rome for about 45 days this year with the explicit purpose to align the telescope. But if anyone here has done instrumentation, they're very familiar with Murphy's Law, which is anything that can go wrong will. And out of those 45 days, only five of them had sun. So this is what my sky looked like when I was trying to align the telescope with the sun for the vast majority of my time there. So the current status of the TSST is that it is still working on being aligned, but it is almost there. So we're hoping at the beginning of next year in January, when I return out to Rome, we can get this fully aligned. Then with those 5 days of sun, we were able to get some nice tests on our H alpha telescopes. We were able to get some good first light images. And again, this is where that roof comes in. I was up on the roof testing our H alpha telescope, and the image you see on the right is taken with our H alpha telescope in April of this year. And we're able to see a lot of great prominences on the limb and in the disk itself, some really great features. And we were really excited to be able to run this test because it revealed to us a few different things we needed to fix up with our focal lens and also our cameras in general. So this was a really beneficial use of our 5 days of sun. So when we don't have sun, a lot of the focus on the TSST, which can't go to alignment, is going to our structural design. And so we're working on building and constructing the box we designed to hold our telescope and to block out anything like dust that we have an issue with in California. So we can then bring that box design over and improve the one in California. We also work on building tiny little pieces like this camera holder you see, and also our final negotiations for which dome we're getting and where we're placing it. So this is the main focus of the TSST right now when we don't have sun, is the final decisions for structure and building and placement. Now, I want to bring my summary of TSST, and I know it's been a lot shorter than California Mojave Solar Observatory, but I want to remind you that's because the focus of this year has been on MSO. It's not that the TSST is any less important. In fact, it's what's giving us a network as opposed to just one telescope. So currently, the TSST is in final in-lab alignment. It will be ideally done in January of next year. And the mounting construction box is currently taking place as well. And then final negotiations for the exact placement of the dome are in the route. So the focus of Gates next year in 2026 will be the TSST. So we're hoping to get both nodes up and running. Now, my final what is what science Gates can address. And I want to start with the science that I'm choosing to address first with our data, which is wave propagation. And specifically, I want to look into those acoustic waves and how useful they are, if they are at all, for flares, like our previous moth data has investigated. But also, is there any mechanical heating we can see in waves, or is there not, which is seeming to be the current status of what's believed. Another thing we can investigate with the expansion of Gates would be our expanding observational heights, looking up into chromospheric observations, which can provide us some more information on different heights in the atmosphere. Another really popular thing right now is to do space weather studies with machine learning and AI, and we'll be producing a very large continuous data set that can be used for these models for training and testing. And ultimately, again, Gates is hoping to be automatic. So it's hoping to do continuous real-time forecasting once we get to that automatic stage. Now, that is not a current goal for the next year of Gates, but ultimately, this is some science we hope to address. And finally, there's much more science questions with Dopplergrams and magnetograms from multiple heights that can be answered that I don't even know the questions of. So that's one thing that I am looking for is if you have an idea for a question that you think Gates data can answer, please let me know, because that's what we're looking for at the moment. Now I want to go on to my final question, which is when, which again is probably the question most people have been most excited to hear about, because when can you use this data? When will it be up and running? So I want to show you a nice timeline that runs from the present day to the end of 2025, or January 26th. And this timeline is set because this is when we hope to have both nodes up and running, but also corresponds to the end of my PhD, which is why we're set at this time frame. And the little flags you see represent what the focus, which node of Gates is the focus at that time, and it also corresponds to where I currently am, coincidentally or not. And so the current status present to January of 25, the last month and a half of this year, is to have that dual channel observing campaign at MSO. We've gotten the calibration fixed up, we have the data transfer and storage, so we want to have an initial 2-height observation data set that we can use. Next year, our focus switches back to Rome for TSST testing and completion, doing on-sky testing in Rome before moving it out to La Palma. But we also want to be doing some analysis on that MSO data that I'll be taking shortly. So hopefully by mid-year, we'll have some nice science out from Gates to show that this is a network that's doing really exciting things and can be useful to you. So the second half of next year, when I return back to the States, we are hoping to do our upgrade on MSO to complete that helium MOF that we're still working on now. So we'll see if that ends up by the end of the year operational or next year operational. So our end goal by the end of 2025 is to have, again, that observing with 3 different heights across 2 different sites, showing that Gates is a network that is currently operational for multiple heights. So I want to end with some concluding points to, again, basically tell you why Gates is important and what it can do for you and what science we're trying to target. So first off, I hope I convince you that ground-based networks can have a really great potential for space weather observation, and that Gates is going to be a really great network for that. And not only that, but MOFs themselves are really powerful tools we can use for these types of studies because of their ability to give us really great velocity and magnetic field measurements. And again, my talk is on Gates, so I want to talk about how Gates is creating a new solar observatory that currently has data taking capabilities and is projected for full operation by 2026. And finally, we're looking for science questions for Gates Gated to investigate. So if you have any ideas for things we can study in Sun or otherwise with Gates, please let me know. My emails are here, and with me asking for you for questions, I will also take any questions on my talk itself. And I thank you for your attention. And again, sorry I was coughing so much.
Thank you. So now it's open for questions. Anyone in the room or online, you can unmute and ask your question.
Hi, Fallon. I'll ask. That was a great talk. Very complete. Thanks for showing the whole scheme of what you're working on. I guess a small point. So you mentioned the sodium is sort of formed at 700 kilometers, but that's very much the line core, right? And
Yes.
the MOF is sampling out in the wings, which is at a very different height and probably isn't as sensitive to the any structures that high.
Yeah, I do get dinged this a lot by my advisors. Not only is it the line core, but it's the line core in the quiet sun. So if we're looking at an active region, it is very much a different height. And you're right that the sensitivity is a little bit different, but that's one of the things that we run with our data tests is what is our resolution still, or are we actually, like, do we know what height we're looking at? So it is different, but on average in the quiet, that's about where we're looking.
Have you done tests with full spectral profiles or simulations to see what you're actually observing? Because I mean, the problem you didn't mention with the MOF is that you're sampling in the wings, but at a fixed absolute separation of those two peaks at an absolute wavelength. So you're not, as the line shifts due to rotation or other reasons, the two wings that you're sampling are different parts of the line profile. And so constructing, and those different parts of the line profile are again at different heights. So constructing those Dopplergrams is not
non-trivial.
It's not what most things do when they're looking at scanning a line profile or getting a spectrum and computing wing velocities.
Yeah, so our wing selector section, so basically where in the wings we're looking at, is set by the temperature of our cell. So we can change it and know where we're looking as we change the temperature if we need to, because the location is changing, like you said, for rotation or whatnot. But one of the things we're actually looking into regarding the helium cell is to do line scanning with laser, simply because we are trying to test, do we need that for laser pumping or whatnot? So that's one of the things we are potentially trying to see if we can improve upon is, can we do scanning so we can look at all of the lines? But you're right, we currently can't. It's set at whatever temperature we have. And so I personally have not done any modeling on the sodium, for example. I have done some on the helium, but that's definitely something I'd want to do when we have actual data, is model what our wings look like so we can have a better understanding of where exactly we're looking.
Mm-hmm. Right, what that phase mixing is, and things like that. Mm-hmm.
But since I've done it for helium, I have the capability of doing it. Right. I just have been spending most of my days with screwdriver.
How long does it take to tune the sodium filter? Could you do it in a few seconds?
By tune the filter, do you mean change the temperature, or do you mean model it computationally?
Well, change the temperature. Yeah, how long?
Yeah, it's a couple seconds. Heating up is obviously a little bit slower than cooling down. Actually, guess depending on the temperature outside. But we go from ambient temperature of about 20 to our operational temperature of 170 over the course of about 5 minutes. So it's pretty quick.
Mm-hmm. Mm-hmm. Great, neat. Thank you.
Thank you.
Any other question? Please unmute and ask. Yeah, please. Yeah.
Hi, nice talk. I just want to know what is the kind of field strength involved in the magneto-optical filters.
Sorry, can you repeat that, please?
Field applied. There's a external field applied in the magneto-optical filters, right? What is the kind of field strength?
It changes for the different lines. I believe currently we're working with 3 kilogauss and 1.7 kilogauss for the sodium and potassium. And our helium, we're working with up to 4 or 5 kilogauss. We use bar magnets to build that.
Okay. Can I ask one more question? What's the kind of spectral resolution that is, that can be achieved with this?
Our spatial resolution?
spectral resolution, like passband of the filter.
I thought I wasn't. So MLS in general can get down to about 60 milliangstrom, which I think in ideal cases ours can as well. Because we currently just ran like the data test for calibration and stuff, I have not measured what our current capabilities are, but theoretically, that up to that.
Mhm.
Obviously, realistically, a little bit less
So around 60 milliangstroms you can take.
in theory, but realistically, I'm not claiming that realistically.
Okay, yeah, thanks.
Any other question? Okay, if there is no other question, let's thank our speaker again today for a very nice talk.